ఏది వాట్
Good morning, guys. I'm so sorry for keeping you guys waiting.
నో ప్రాబ్లం భయ్యా.
So, happy Independence Day, guys, and happy Raksha Bandhan. Today, we'll work on the California housing price prediction problem. Right. The data set is available at Kaggle. So, if you're following along with me, I'll send you the link. You can download the data set from in here. Right. So, I already have this housing.csv file downloaded in here on my current working directory, but then you can download it's not really that big of a file, about 1.36 MB, so it shouldn't take much time. So far, we have covered all the major regression and classification algorithms. So today, and we have also completed one problem statement using for classification. So today we'll focus only on regression, like problem statement. So the problem statement here is we have a data set of all the housing price and all the housing attributes, some of the attributes like the area wise attributes and the house wise attributes, some features in the data set like how close it is to the ocean, what's the mean median housing value, the median income of the people living in that country, the overall population, the total bedroom rooms, the age of the house, like the median age, and some location coordinates like latitude and longitude. So these are the fields within the data set, and these are also going to act as features. We'll also do some bit of feature engineering, right? So this is there. Now the idea is we'll come up with a prediction wherein we'll be using the regression techniques, right? And we are supposed to predict the housing price for the California region. So whenever there's a new attribute with all these features, you would be your machine learning model or your regression model would be able to predict the uh, right housing price uh, for that new house. That's the idea, right? So we'll quickly import the necessary libraries. We'll require pandas and numpys, that's for sure, and even matplotlib for some of the plotting or visualization needs, right? Mat, okay. Let me know if you guys have downloaded it. So because I already have this file in here. Right. So I'll quickly um, load the data set into pandas data frame maybe. So, and just to see like the first three rows, how exactly the data looks like, I'll do a head method. So we have some bit of information about the latitude, longitude, the housing median age, the total number of rooms, within that location coordinates, right? The population, the household, the median income, and median income is, I believe, in US dollars. Median house value is also in US dollars, right? You can get more detailed idea about each of these fields from the description in here, right? Then, right, so how close it is to the ocean proximity, whether it's near bay. In fact, so every time you get a new data set, your first task should be to explore the data, how what exactly is there, like how the data looks like, how many instances are there, how many features are in there, right? So we'll first do some bit of investigation, maybe how exactly data looks like. So maybe I'll do an info method. So to get an idea of how many rows are in there and then what their types are. So there are total 20,640 data instances, out of which there are some missing values in total bedroom, and everything is of the type float except for ocean proximity, whose type is object, which we can tell by seeing at the data. It's all string. It's not numbers or floats, so that's why it's of type object. But this is like a good practice data set because most of it is already there. We have like very less of missing values, and that too only in total bedrooms field, right? So yeah, if I'm to write down the observation, I would say there are 20,640 instances, right? And total bedrooms has only 2433 non-null values. That is 207 values missing, right? Now let's also explore what all values we have in this string type, like ocean proximity. Like so, if you remember the value counts method that we talked about when we were discussing pandas and NumPy library, it basically gives you a count of all category that's there within that field or column. So I'll call the same value counts method for this particular field, ocean underscore proximity, right? And we have like five categories in here, right? Less than 1 hour, ocean, inland, near ocean, near bay, island, right? And there are about only 5 instances with ocean proximity as island. Nice. So let's also look at all the numerical attributes and like the rest of these, right? To get similar to info like method, but then all the statistical measures like what's the mean, median, first, second, third, fourth quartile, we call the describe method, right? So I'll do a describe on the entire data frame, and we have like for all the numerical attributes, the mean and median values, and also their second, third, fourth quartile, the min and max values, right? So the maximum any housing value has gone is 500,000 US dollars, right? Minimum being about 14,099 US dollars, right? Now let's look at these numerical attributes, like at least all these. How many fields are there? Actually, 10 columns. So we have one of type string. So let's look at all these 9 numerical attributes, how the data is actually dispersed. And I think I gave you guys this idea in our previous class. The best way is to put them into pandas and then do a histogram plot on the entire numerical features, right? Now to plot histogram directly using pandas library, you can call the hist method and then just specify the bins that you want to create, how many buckets or bins you want. So let's say I want 50 bins, right? And yeah, let's just do a plot show.
Hi, sir. Bins means what, sir?
Bins basically means bucketing. So let's say you have 100, for just a hypothetical example, let's say you have a number ranging from 0 to or 1 to 100, right? And I ask you to, boss, divide these numbers into 4 buckets, right? You would grab every number from into 25 values, bunches of 25s, right? 0 1 to 25 will be in one bucket, then 26 to 50 will be in second bucket, right? 51 to 75 in third bucket, and 76 to 100 in fourth bucket. Basically, I'm dividing them equally. So let's say we have a linear data, okay, and it's all from 0 to all the way to 100. And I ask you to divide all these values. There are different values lying on this line, right? All 100 values. And I ask you guys to divide the entire line series into 4 groups. So ideally you would, create 4 equal size groups at 25 quartile, right? Like this one would have 25 values, first bucket. Then this one would have the next 25 values. So I'm basically creating these bins, 4 bins. Now, if I tell you to create 6 bins, these values would get reduced. So bin basically means clubbing them or grouping them into equal numbers. And whenever we do a histogram, so let me clear this, all this. The reason we needed to specify bins was because whenever you're doing a histogram, you need to tell how many data instances to keep in one bucket. So let's say if I'm plotting every instance, it will come down to like single lines like this, right, for every instance, and you won't be able to better get an idea of how exactly the data is dispersed. So we group them together, like consider similarly, like taking 4 quartiles, so group them into 25 instances together. Okay, you will have something like this that looks more readable, right? You can make more sense of. So every bar in this histogram has about 25 values if I set the bin size to be 25, right? And ideally we start with bin size 50, or you can even take 100. There's no specific stated rule that you should always take 50 bins or 30 bins or something. This is very small, so I'm increasing the figure size in here. This one looks much better. So every bar, it's still very small, but if you're able to see, like, if consider this bar that I'm pointing out with my cursor, this bar would have like 50 values. This bar would have some values that, so that the entire data on the series is distributed into 50 buckets actually. So it's not necessary that this would have like 50 values. Basically, it's creating 50 buckets, like how we created 4 buckets, each one having 25 values. So out of 20,000, how much was there? 20,640. it's going to create 50 bins. So some maths in here. So if I have like 20,640 divided into 50 subgroups, each group has 412 or 413 about data instances each bar. Cool. So now if we let me zoom out, or maybe let's reduce the size a little. Let's keep it the same. I will scroll the page. So if you see the value, the median house age is kind of dispersed between 0 to 40. So like most of the houses are between 10 to 45, with few houses that are like exceptionally standing out as outliers. You see this straight line in here. So this means there are some houses that are above 50 years, and they are like exceptional ones in here, right? Household. I'm not sure what household exactly means. So household is the total number of household, a group of people residing within a home unit for a block. Okay, so that's usually like less than 2000, with some exception. Like so there are some people in here. See, there are some people in here between 2000 to 3000 as well, right? And if we latitude and longitude, just because they are numbers, it's dispersed on the histogram, but no, there's no way you can really make sense out of it. But then you can say like most of the houses have latitude close to latitude coordinate 34, between 32 and 33 and 35, but that's totally noise information, not really helpful to us. Let's look at the median house values. So just like median age, some house values are exceptionally high, like some of the houses are exceptionally costly. There could be some factors that they may be in some posh, lavish areas or maybe close to ocean. Remember, we had an ocean proximity attribute. There could be a number of factors, right? The median income looks pretty much normalized. Well, not really normalized, but then it's in a very well, bell-shaped curve. So we can say like the most of the people are earning between the scale 2 to 4. I wonder what 2, 4 exactly represents. So let's look at the definition for median income. So So the median income for household within block of houses measured in tens of thousands of US dollars. So it's basically tens of thousands of US dollars. So 20,000 US dollar to 40,000 US dollar. That's what the average people are earning in that in California, right? And the population, average population is between like 0 to 2,500 maybe, or like less than 0 to 2,500, right? Total bedrooms are less than 1,000, which is obvious. I don't know who's having more than 2,000, 3,000 bedrooms in their houses. But that's okay. Total rooms. So that's how exactly you get a sense of all the numerical data, like how the data is dispersed, right? Now, remember the kinds of sampling we discussed in classification and also in regression. We have like you can, since the data is not always normalized, it is always suggested that you do stratified sampling whenever you're creating test and train set, because the data set is also quite less. 20,000 instances, not really a, I mean, I would say it's a medium sized data set, but not really, we don't really have like huge data sets. So it's always good that you maintain the proportion of all the values. So it's suggested that you go about doing stratified sampling, right? Now, median income sounds like a pretty, just by looking at the problem statement, we are supposed to predict the house prices. There are a couple of features you can actually think of right away, right? consider yourself as the domain expert. You're like someone who's very good into real estate industry, right? You have a very in-depth knowledge. Just by looking at all these features, you can tell, okay, maybe we just need to take into consideration so and so features. We don't really require all the 9, 10 features, right? But then we still have some idea, like if the people are earning X amount, the kind of houses they can afford, right? So if the majority of the people are lying within this salary range or income range, the housing price range could be somewhere, relevant to this. So in fact, if we, elaborate more on the median income, we might be able to look at it. So, well, at least now we know, like just by looking at it, that median, and consider this a scenario that you're working with a domain expert, and he told you that median income is like one of the most important features. Or even if you're not working with any domain expert, we know that how much a person is earning could be an important factor to decide the kind of houses they can afford, or if the average people are earning X amount, what should be the average house price values, right? So median income looks like an important feature maybe, right? Now we need to ensure that this, at least this of all the numerical attributes, at least the median income and all the important attributes, like I even feel total bedroom could be an important factor to decide if it's a 2 BHK or a 5 BHK or a single BHK. The housing prices should be different, right? So at least among these attributes, the sampling that when you're creating the training set and the test set should be stratified, right? These things you won't get beforehand. No one would tell you. This is something you have to think of on your own, and this is something you'll develop over the years of experience of practicing. Well, you don't really have to have the experience of years. The more you practice, the more you'll get the better idea of where exactly you should be using what kind of sampling. So, well, there are some people earning exceptionally high. That's okay. Let's create an income category because we would still want this to be normalized. I can see some skewness on the right hand side. It started off very well, but then it ended up being very skewed in here. So, and in fact, if we can, even categorize it into a category like thing, it becomes easy. Like people earning medium scale, high earning people, and low earning people, right? So maybe we can create like 4, 5 categories like that. The best way would be we could do, just cut short these by some scale, right? And that scale will be same across all the 4, 5 categories that we'll be creating. And then maybe we'll do a roundup using floor or ceil function, because maybe while cutting short them uh, in some range, we might have some fractional values, right? So maybe we'll use the ceil function actually. So that and if you don't know the difference between these two rounding approaches, the ceil and the floor, do read about them. These are mathematical norms of rounding. Calicro and floor, right? So ceil is, I'll give you a heads up. Like ceil is basically if you have values like 2.7, the ceil would return like 3, and the floor function would return like 2, right? So whenever you're rounding up, you should know like what kind of approach you're using in rounding up, whether it's a ceil or a flow function. All right, so let's divide these into 5 income categories. So we'll divide everything by, if this is range from like 0 point maybe 3 to 14.5, right? If I am to put this into equal 5 bins, right? I'll divide maybe by this much, this much, this much. So maybe like 1.5 times, right? Starting from here all the way till here would be like one chunk, and then here second, third, fourth chunk, fifth, and let's club everything like more than fifth chunk into fifth category as the highest. Everyone earning in 10,000 or 40,000 are maybe categorized as like people earning more than 10,000. Just one category is enough to state their income category. So I'll divide. I'm basically limiting the income category, right? So let's call it income cat, right? And we'll use the numpy ceil function for rounding. Sorry, it's median income. Oh, 1.5. So we are dividing every chunk width by 1/5 and then doing a ceil function. And let's also, push everything greater than 5 into category 5. Fifth category, right? So we'll do that. Income cat, and we'll use the where function of now pandas. So the general syntax is where condition, then true statement, comma, false statement. If you want to look at it, just tap in shift, double tap. You'll get the idea. You're supposed to first parameter is basically condition. The second parameter is basically the cases wherein your condition is not matching. By default, it's set to be nan. And then the cases wherein it's all false, like your condition is not really satisfying to true cases, right? So wherever, oops, housing income cat is less than 5, others as 5, wherever it's false, and let this be in place equals to true, so that it happens spontaneously and in place. All right, so now that's done. A quick look into it. So that's our income category, right? Now that we have this categorized, let's now do a stratified sampling. So we'll import the stratified shuffle split library, stratified shuffle split class actually, from a Skillathon model selection library. So it's tab, okay, tab. Okay, I'll write it down. Stratified SHUFFLE split. We'll specify the number of split. In our regression class, when I was explaining to you how to exactly do the stratified and random sampling, I just gave you guys a pseudo code line, pseudo lines of codes, like how exactly we do the test and training split. We'll now be actually using it. I'll set out the test size to be like 20%. So that's 0.2. And we'll give out some random seed. So random state is set to 29, right? Then for train index, why divide by 1.5 and not by 2 or 3? You can divide by 4 and 5, any number, Kinjal. I just wanted to create 5 bins out of these. So I assume like the if I am to divide this, if you look at my cursor right now, if I'm to divide all the values from here to here into 5 categories, I would have to like split somewhere like first bucket should be split somewhere in like here, and then second maybe in here, third in here, and then fourth in here, and maybe in 4 5 I'm capturing like most of it. You can even divide it into 2 or 3. Feel free to create as per your will. You just need to change in the values in here. This is basically the scaling that we are doing, right? Feel free to try out other numbers as well. And this is actually wherein you will be experimenting with the values and the data sets. Nothing is pre-stated to you guys. So whenever you're working as a data scientist and you have some data set and some set of instructions, feel free to try out and experiment every possibility you can. I just clubbed these into 1.5 bucket bench size because I already know how well it categorizes into 5 categories. But you can still divide like into even 4 categories is ideal. So if you have to divide it into 4, I would split somewhere in here 1, 2, 3, and 4. But then if you see the third and fourth are like very sparse. At least the fourth bucket or bin that you will be creating, the fourth category would be like very sparse. Very few of these would be in here. So maybe you can create like 2 or 3 categories. So if you have to create 3 categories, I would divide it by somewhere in here first cut, and the second cut somewhere in here. And that's also, I would usually divide it by 2.5 maybe, right? The first cut should be in here, and this is like 2.5. If this is 1, this is 2, half of it would be here. So this is 2.5, and then the next 2.5 would be in here, and then everything in the third bracket, right?
Sir, what is difference between train test split and stratified shuffle split?
Okay, I'm not sure if you're present in that class. So I gave out an example of survey of 1,000 people. Remember? I'll explain again. No problem. So whenever you're creating a training set and a test set, you need to make sure that your training and test set that you created has like the most of data variety in it. Otherwise, let's say, again, I'll take the same example. This is pretty much the best example to explain stratified sampling. Let's say you're the owner of a company, okay, and you're supposed to do a survey for your product, and you're going to different countries, and then from each country you're picking up 1,000 people, and then based on their opinion about your product, you're deciding how exactly is your product performing in a country, right? Now if you're taking just random 1,000 people, it's random shuffling. You're out of n population of a country, you're just picking up random 1,000 people. It's random shuffling. When you're making sure that the gender proportion across the population, like if the country has a gender ratio of 60 by 40%, 60% male and 40% female, and you're maintaining the same ratio in that random 1,000 people that you're picking up for your survey, you call it stratified shuffling. You're basically maintaining the proportion of each class out of the entire data set. So when I'm grabbing 1,000 people that represents a country, and I'm making sure that the number of males and the number of females are in the same proportion with respect to the proportion they have overall in the country, I'm maintaining the proportion for each class. I call it stratified shuffling, right? Now coming back to split, when I'm doing random shuffle split, I'm basically splitting the entire series from 0 to n or 0 to 1000 or whatever the limit is into some random bunches, right? And then I'm grabbing each index and then putting, separating the entire data frame based on those indices, basically slicing. And when I'm doing this in with respect by maintaining the proportion of each class and then splitting up the entire series from 0 to n, I call it stratified shuffle split. Bas, that's all that's there in sampling and shuffling. I hope you got some idea out of it. Random is wherein we are just picking up randomly, and then stratified is wherein we are maintaining the proportion of each class. Cool. So I'll make sure that when I'm splitting, it maintains the proportion across these between the housing and the housing income category, so that every class in the income category, that 5 categories we created, are in the same proportion with respect to the entire housing data set. And now that we have all the indices, basically numbers from 0 to n, right? We'll just use them as indices for our pandas data frame and then slices up into training set and testing set. I'll call it strat training set. And I'll use this numbers, these random numbers as indices. And similarly, I'll create the test set. Okay. That's because it's called n splits, not n split. So I'm basically creating one more split out of the entire data set. So when I mention one, it's going to create 2 subsets. I'm splitting it in by one more data set out of it. And that test set is going to be like 20% of the entire corpus, right? All right, now that we have this, let's look at distribution of all the instances that's falling in with respect to each class in the income category, so that we know how stratified it is, or like at least out of all the 5 income categories that we created, how many or maybe what percentage of the total rows are there in it, right? Now to get the percentage of rows, we just need to divide them by the total length of the housing data set for by the length of each by the length of the rows within each category. Now to get that, we know there's a straightaway method of value counts, right? We know how many rows are in there within each category. The moment I divide these with the total number of rows, we'll get like the proportion. So this is the proportion that's there in the housing set, and that's maintained. This is the proportion that's there in the housing set. Now we'll check this for the training and maybe test set, right? Let's pick test one now. Copy paste. Right. We'll divide it by the total length of the test set. And if you see, the proportions are the same. And that's stratified sampling. Now, again, since we discussed this, I'll tell you the ground rule. Whenever you have a small or a mid-range data set, or a data set where you have less number of features, like anything less than 15 or so, always and always do stratified sampling, right? Because if you do a random sampling, chances are you might miss out some cases where the one particular class has very few instances. I'll write down a note in here as seen above. The proportions are maintained is set using stratified sampling. All right. Now the test set generated has income category proportions, very identical, or in fact, pretty much no. They are pretty much identical, not really like exact, but then the proportions are pretty much same: 35%, 31, 17, 11, and 3%. Right. Now the important question is why in particular we go for sampling like this. So I'll write down that as well. Because the feature, I'll call it feature space, basically representing the number of features, are less, and also the instances, or maybe the size of data, or it's also because it's a mid-sized data set and we don't want to miss out any class. Right? If you wanted to do a random sampling, chances are you might miss out at least this one class because it's like very less comparatively, like just 3%. In fact, let me show you guys how exactly things would differ if you do a random sampling and then compare it with the proportions in the stratified sampling and see how many, across each class of the income category, how much, how exactly the proportions are maintained. So experimenting with random sampling now, right? So I'll import in again from the model selection random shuffle split, or maybe it's just a simple train test split because that is also like random sampling. In fact, I'll import train test split only. So yeah, now I'll call it train set, test set, train test split. I'm passing in the data set. I'll specify the test size 20%, and I'll keep the same random seed that is under random state, same seed 29, right? And let me, add a comparison like thing. So let's create a function, in fact. So you can try out different, random seed combinations. Or even if you try out different, binning logic, like instead of creating 5 categories, if you try out something else, you'll just have to call in the function. So I'll call it IncomeCat prop. And we'll pass in the data. Or let me give it the full name. Income category proportion. Right. That's a correct spelling. PROPOR. Right. And this would be data income cat value counts divided by the length of data. Right. Now comparing proportions, I'll create a data frame let there be one for overall proportions, right? This is going to be my income cat proportions, and I'll pass in the actual housing data set. So there will be one column with overall proportions, and there'll be one with randomized proportion. I'll just call it random, right? Again, calling in the method, and here I'll pass the test set, right? And then I'll call this one as stratified. And here I'll pass in the strat test set. So yeah, in fact, let's also do one thing. Let's sort it by values or sort it by index. So we have 1, 2, 3, 4 all here, in a sequence. And in fact, let's make it better representing it. So I'll convert these into percentage error. Like I'll calculate the percentage error, how much of it is actually the percentage of it's actually missing out. So I'll create 2 more additional columns. Random percent error. Yeah. So this will be 100 into random divided by overall, right? Minus 100. Because we want the error, right? How much it's missing out. I'll do the same way for stratified. So yeah. Okay. Overall. Oh, okay. Overall props. So there you have it. I'll remove this. So when you do a random sampling, you have like a huge error rate for class 1, right? Most of it is missing out because it's very less in sparse when it's all sparsed out, and when you see it density wise, it's just 3%. So if you do a random indexing out of it, chances are you will miss out most of it, and that can be seen in here. Like we are missing like 7%, nearly 7% of it, right? And if you see the stratified error, that's quite less. So 0 point something less or 0 point something more, I would still call it like, somewhat equivalent to the actual overall. There's very less error with respect to the overall proportions. So that's why you should. So this is the answer to your why. Cut. Or maybe I'll keep it here. Or at least you'll get the idea. The answer to why your why is in this matrix, the data frame that we created here, right? The test set generated using stratified as is pretty much identical in terms of proportion to the overall data set. Now let's but yeah, ideally you would want to remove the income category, so that the data set is back to its original state. We just needed to have the data set stratified while creating the train and test set. We don't really require this bucketing. We would actually require the actual income categories in here. The buckets we created was just to have this, proportions maintained across train and test set, because we felt median income is, somewhat an important attribute or important feature for any prediction, right? If a person is earning X, the kind of house he can afford, it's kind of stated obvious here. So now you would actually, ideally want to remove that income category, because we just had this for creating a stratified sample. So I'll just do a drop across all the training and test set for items and train set and test set items dot drop what income category. Make sure to specify axis equals 1. That basically means columnar operation. So we don't want to remove row, but the entire column that says income category. And do specify in place equals true, so that the operation happens right there and then and there. So, all right. Now let's visualize all this, all the data instances across the locational attributes that we have, the latitudes and longitude. Like how many data instances are there across some pair of latitude and longitude, right? And then we'll even, try to plot this out on a map. And if you had gone through the kernels, because I already specified that we'll be doing this problem statement, if any one of you have already tried this and had gone through some of the kernels, you would know like every other notebook they are using this same plotting approach. So let's create a copy, because we don't want to mess up the actual data set. So we'll create a copy, and in fact we don't really need this one. We'll use the stratified data set now, and then let's assign it to the housing variable itself, right? I'm creating a copy of the actual stratified training set and storing it under the same name. So I'm basically replacing the data under this name, housing. And let's do a plot using panda's own library. I want this to be a scatter plot, and for the x and y's I'll specify longitudes and latitudes. Right? So we have a huge chunk of rows that has latitude and longitudes somewhere in here, right? There are huge data points in here and here. Well, there are some data instances passed on the other edge. Now, but then this one still doesn't make much sense. Or maybe if we set out an alpha size, so that we'll get a better idea of the density. So if I just specify another parameter, alpha maybe 0.2. Let's keep it small, like 0.1. All right. So the denser values are in here, and the lesser values are, with the dimmed out way. The other thing is you can, include in a third axis into this plot, like other than the x and y, you can include the population as well. Like we can set out these data instances to be represented by, circles or some shape that gets changed with respect to the population. So the more the population, the bigger the data points are going to look like. So if I'm to do that, I'll change these. In fact, let's keep it a little higher this time. And for the size, I'll use the population size of these circles of these data points. Population. Was it population or populations? Population, right? Population, and Let's add in a label. Population. In fact, let me just put percentage of population instead of the actual discrete values. Let's keep a percentage. So everything is scaled between 0 to 100%, right? And let's also increase the figure size this time. Maybe 12,8, right? And we would also need to specify, I mean, if we want, we can use one more attribute, the house values, right? So that's by the name median house value. We'll use that for the matplotlib CMAP marker, right? So for the marker, we'll use median house values, house value, right? We'll use the CMAP of matplotlib for the colors, right? So I'll use get CMAP and use the jet type. There are many options. Jet is basically very bright green, red, and blue colors. You can use any. I'll show you the other options. In fact, I don't even remember all the names. I pretty much use CMAP with jet all the time. So there's Viridis, Plasma, Inferno, Magma. You can so these are different color maps. The jet has like pretty bright blue, green, red colors. So you feel free to try out any color map you want, right? And yeah, and do make sure to have your parameter called sharex set to false. That is something that's like a rule or something that should be there. Otherwise, it all messes up. So plot the legend also. Right. So now the redder ones and the bigger circular chunks basically represents the population, and the red color basically represents how costly the houses are. So if you see, the most of the costlier houses are somewhere in here where my cursor is moving right now, and the less price houses are at the far end, rear end, right? These would be like the pretty much the average house values, and they have like average population density as well. There's a huge population in here. The huge population chunk is staying in here, right? In here. Now, the moment you add this to the California map, because it's all in latitude and longitude, you'll get a better idea of in the map where exactly each of this is falling to, right? And you can pick out any map, right? And now if you see the map, it's all shaped in the same way how our data looks like when dispersed, right? It's all scattered somewhat similar to how the country map is, right? Now I already have this PNG image downloaded, and you'll find it even in the notebook kernels on the Kaggle. I in fact grabbed it from there. But then you can import in any of these maps. Just make sure it's a PNG format. It's easier to know. Do a subplot over top of it, right? And the way to do it, and this is again not necessarily, but then if you're really into building a more enhanced notebook while you're exploratory analysis, so the way to do it is here. I'll show you. So we'll plot everything we just did on above. In fact, I'll just grab this. And you know what? Let me add in. Okay, I'll leave. Copy. paste. Right. And now we'll include the image. So I have the image in here. And for the extent, we'll set it to be -124. We'll keep the same range, -124 to 114, or maybe less, like 113, -113, somewhere in here, right? And this would be, so this have like 2 units difference. So this would be like 32 to 42, or maybe a little more than 40, 42.5, 32.5 to 42.5, right? So we'll set the extent minus 124 point, or let's keep it just 124, right? Minus 113.8 maybe, and this would be 32.5 comma 42 point maybe 1 or 0.5, right? Setting out an alpha value, and color map to be again jet. So yeah, some labels. So this one is our X is actually longitude. So right, and to increase its font, copy, paste. This will be our latitude. Set a, now for the prices, it's median house values. So we'll set out a tick value, right? Like tick prices in here instead of these 1,000 showing up. In fact, let's see how exactly it looks like as of now. Okay, I'm missing out something. Image data cannot be converted to float. Maybe I'll store it as a variable first. IMG. I should have done this before, but you're supposed to include, load an image using the MP matplotlib img class. So I hadn't imported that before, so I'm importing that now. Matplotlib dot image as mpimg. Read, and this is where I'll specify the image. All right. And here I'll specify that image placeholder, California IMG. Okay, maybe it's moving out a little. If we set this to be 0.55 maybe, right? Let's reduce this to 4. Still much better, maybe 6. Well, so now you have an idea. Anything? So all the red ones, the high cost houses, highly priced houses, are like the ones close to the sea, on the seaside, seashore, right? So let's reduce this again. Yeah, better. So that's how you can do. You can enhance your notebook further. Now, coming back to the problem statement. So the idea is we are supposed to predict the house prices, and we are the first thing first, before building any model, we need to decide on what factors are actually influencing the y label. And by now, if you haven't figured out, our y label is the median house value. That's what we are supposed to predict. In fact, if you can change this to, you can add in an X tick to the color bar that represents a dollar in here, like a dollar symbol, right? But okay, let's not waste time on that. So to get the idea of what features are actually, influencing the median house values, we'll look for correlation. Now, since the data set is not really that huge, it's easy to compute the standard correlation coefficient. If you're not familiar with correlation coefficient, here's the next thing in statistics that you need to be reading about. Do read about Pearson's distance correlation. It's not even statistic, it's mere maths, right? It gives you how exactly values are correlated to each other basis on some distance measures. So for now, to give you guys an idea, we are trying to predict, or we are trying to come up with a scale for our judgment, like how exactly each of these, where is that? Each of these attributes are, somewhat relevant, related to the median house value, the one column we have. So basically the relation of all the columns with respect to the median house value column, right? And the measure we are using is Pearson's distance correlation, right? Now pandas already has this through a method. It's called core. So if I do a housing dot core, I'll basically get the correlation for everything with respect to each other, right? So I'll create a correlation matrix. In fact, core matrix. I'll assign this to this name, and then I'll look for correlation matrix with respect to this median house value. So now everything will change with respect to the median house value. Sorry, this one here. Right. So grabbing all the values in the matrix and then sorting them out. Matrix, grab the median house value and then sort by values in descending order, maybe. Yeah, in descending order, like the important ones showing up first, right? So there we have it. So all these other fields have about, so median income has about 69% is somewhat 69% correlated to the median house value. Total room is a factor that's constitutes to like 12% of the correlation with respect to it, right? So all these numbers basically represent how they can influence the actual median house value, and anything that's in negative is showing basically how the median house value is independent of these features. They hardly constitute to any change in the median house value, right? But then the median income See, now hypothesis, the initial hypothesis that we picked, that median income could be an important factor. If we know a person is earning X, we get some idea about the kind of, you know, houses he can afford. So median income basically constitutes like 60% of, you know, the change, and that's happening in the median house values. Now, so I'll add a note in here. Looking for correlation right, and this, to be specific, this is by default it's Pearson's distance correlation. Pearson's distance correlation equation, right? Pandas has core method for calculating correlations. All right. And a side note that it's always between -1 and 1. -1 and 1. -1 basically like representing less correlated, 1 being highly correlated, right? All right. Now, that's one way of saying the relation between the features with respect to a y label. The other approach is that you know, plot out everything and scatter it out with respect to one another. So I'll do a scatter plot between median house and median income, and I'll see how the data points are dispersed, right? Like something as we did in the histogram, I'm sorry, right? We were still able to make out some sense out of these histogram depictions, right? The other way is you can disperse out all the data points with respect to, you know, two values in the x and y planes, like population versus total bedroom, or if you're, you know, very specific with median house value, always have median house value versus latitude, median house value versus median house age, right? That's the other approach. So I'll show you the other approach as well. But then the problem with that is the number of features you have, it's gonna increase to like twice its time. Yeah, power 2. Basically, if I have like 3, 6, 3, 9 values, oh sorry, they're actually total 10 columns. So I'll basically have 10 power to 100 scatter plots, which is, you know, quite impractical. So the moment you have got the core, so since we have this correlation, let's just pick few of these just to show you guys how the other approach, you know, looks like. Approach is to plot them, or approach to use scatter plot in A versus B fashion. Also, problem with this is that if there are n features, for n features, there will be n square plots, which is impractical. But if you are sure of some feature values, you can still do it. So let me pick up the median house value, median income, total rooms, and median house age, just these 4, right? House value, total room, median houses, and of course our y label, and then see how exactly the, you know, the plot looks like. So I'm picking up 4, so it's going to be a total of 16 plots, right? I'll name these as testing now. Important attributes, because they are kind of important. Even with the correlation, we have already got an idea. I'll store these labels in a list. So median house value, median income, total rooms, and we have median age, housing median age, right? Now we'll use the pandas scatter matrix, and for that we'll have to import the scatter matrix, and it's there in pandas plotting library. So from pandas dot plotting import scatter matrix, and then we're gonna call the scatter matrix with these important attributes. Housing, slicing on these important attributes, the entire housing data set, and yeah. Now let's specify a figure size. Otherwise, it's gonna be very squeezed out. I'll show you how exactly it would look. See, so I'll set out a figure size 12,8. Let's see. All right. So now we have all these 4 important attributes plotted with one versus the other, right? So we have median house value versus median age. Wow, this doesn't make any sense. So, but then most of the values or the data instances are somewhere in here. Median income versus median house age, total room versus median house age, and then this is median house only. Then we have total room versus median house value, median income versus total house value, right? Now, if you see the median income, the important attribute that we have, the hypothesis we have been taking initially, it has like there's some bit of linearity in here. It's increasing like a little bit upward as the median house value is increasing. The income range is also increasing, right? If you wanna, if we plot it out separately, I'll keep this one as income, the X, for the Y, median house value. Let's see. Okay, we didn't know that. Oh yes, so there is a bit an outline here. If you can see, there's a solid line in here. That's why there's a solid line when we plot it. We just changed the X and Y coordinates. That's why it's appearing on the top now. There is, so this is basically because there's some bit of stagnation in the income category, and even when we are clubbing this into 5 income categories, we were considering we were taking the hypothesis that anything above some X value will be categorized as one category, be it whatever value it is, right? If I, no, let's zoom in a little so it's more visible to you guys. 0 to 16. Yeah. And 0 to 50,000. I'll keep it 55. How many zeros are there? 550,000. All right. Much better. So now, we kind of have a hypothesis, coming out, very well. Like everything that we thought of, is showing up in the data. Like median house value is, or median income is kind of like a very, important attribute. The total rooms and the median age are also like kind of important. So let's create some more features, because just based on 2 3 features it's hard to come up with any machine learning algorithm, or to actually teach a machine learning model to come up with some prediction. In fact, there's a room for a lot of features you can create on your own. I even gave this as a hint in a previous class when I first introduced you guys to this problem statement. We have total rooms, we have population, right? We have household, that basically tells you how many people are living in there. You can kind of create a feature that says the number of rooms per household, right? We have total rooms and we have total bedrooms. You can create a feature that says bedrooms per room, right? And there could also be something with respect to population, like how many people are staying and the kind of household that's there. So something like population per household, right? So this is what we call as feature engineering. Someone back in some class asked how or what exactly is feature engineering. Coming up with your own custom features is basically feature engineering. So we'll experiment with some of the attributes that will come up with the combination of other attributes. This is basically extrapolation in terms of statistics. Statisticians call this approach as extrapolation, right? So I'll create these 3 features, like the bedrooms per room, and what else did we say? Population per household, population per household, right? We also rooms per household, right? Let's create these 3 features and see if they add some bit of dependency to the median house value. We'll see it through the correlation matrix again, how exactly they contribute to the actual y label, right? Let's create some custom features first. So bedrooms, I'll call it bedrooms per rooms per room. This would be housing. My total bedrooms that's out there, oops, right, divided by of the total rooms, right? This is basically we are saying whether it's a 2 BHK or a 3 BHK, like out of all the total rooms, how many bedrooms are there, right? We'll create another feature, and that is population per household, right? Population per EHOLT household. This is going to be population divided by the total household, EHOLT. Okay, and let's create another feature that is for rooms per household. Was it total rooms or just rooms? I don't remember. Total rooms. Right? Now that we have 3 more features, let's compute the correlation matrix again. right? And again, we'll plot it out in descending order with respect to median house value. I'm sorry. Sort by values, ascending equals false. Well, median income. So this one, I'm sorry. This is one of the features that we created that constitutes like 15% correlation. Then population per household doesn't make any sense. But then okay. Uh, then the other feature we created was rooms per household. That is there. Bedrooms per room. Oh, that's also like quite a negative. Not bad. The new, bedroom per room attribute is much more correlated, but then, kind of in a negative way. So the houses with, lower bedroom and total room ratio are, supposed to be more expensive. Kind of in a reciprocated way they are related. So if this one's higher, the other one's gonna be low. So if this is quite low, the median house value is gonna be more, right? Okay, I'll add in the observation. So, okay, the new bedroom per room is, well, it's highly correlated but in a reciprocated way. So, is highly correlated but in a reciprocative way to the uh, median house value. So the houses with lower or lesser bedroom to room ratio will tend to be more expensive, right? And the number of rooms per household uh, is also more informative than the total number of rooms all alone. In distinct, observation. So yeah, total rooms is like 12% correlated, but then the rooms per household is like kind of more correlated. So you can make out of the sense out of it. So it's basically how exactly they are correlated, like whether there's a direct correlation or there's a reciprocative correlation. So this one's quite high, 0.2, right? 0.25. Let's see the rooms per household with the median house value, just to get an idea. For the X, we'll use the rooms per household. For the Y, we'll keep the median house values, right? Wow. 5 and 0,52 or 520,000. Oh, so there you have it. They are also kind of correlated. As the rooms per household ratio increases, the median house value is also, decreasing kind of. Basically, the lesser the rooms per household, the more the median house value is there, right? So that's that's the other way of seeing the correlation between the other features and creating your own custom features and seeing how they exactly constitutes to the y label, the median house value, and if it's actually stating out any importance, you would take into consideration while building a machine learning model, or otherwise you would just neglect it. And this is, instead of doing so much of hard work, the other approach is you just put in everything to a tree based algorithm like a random forest or descent tree and then grab the feature importance. That's also another way, but we'll look into all the approaches. We have already seen how to get the feature importance. So let's do, since these are all also like numerical attributes, let's see the mean, median, and the first third quartile values across these custom features that we created. Now to get the idea, we'll again do what we did earlier, like we'll call the the describe method, and we'll see on the housing data set, and we'll see how exactly these values are distributed. So the average rooms per household is, that is the mean is like 0.8. Okay. And the population is like 0.69. Okay. Just to get an idea of how exactly the values are. So we pretty much have done all the exploratory analysis. I don't think there's much to explore. Let's start preparing the data for machine learning model. So far we have only been experimenting and exploring and exploiting the data set. Now we'll actually start preparing the data set. Preparing the data for ML algos. Right. So we'll grab this stratified sample that we created, and we'll only use that. I'm, doing a reassignment of stratified train set because we have kind of, changed quite a few things. So I'll grab the fresh training set, the first fresh stratified training set, and I'll drop the Y label actually, because we don't want our machine learning model to have the Y labels beforehand. We'll store it somewhere else in a different value as labels maybe. So median house value is dropped, and I'm assigning everything back into housing, and let me call it housing labels, right? Strat train set, and just the median house value, and I'll create a copy so that anytime you do any change or in anything, it shouldn't change the actual values. So let's grab the copy. All right, now we have our fresh data loaded in housing and housing labels. Let's start with a bit of data cleansing. So we know total bedroom attribute has some missing values. Now in order to fix this, we can either get rid of all the corresponding districts wherein it's all missing out, right? If I show you guys again, housing.info, we had some values missing out in here. 16,349. Some values are missing out in the total bedrooms. One way is you can get rid of the whole attribute, like remove total bedroom as a whole, right? The other is you set them all to be 0 or the mean or the median, right? That's kind of like the ideal approach. if since it's a numerical attribute and there's just a few of these that's missing out, so we'd rather impute the with the median values actually, right? So one way is you can you can calculate the median on your own, right? And then replace all the values that's missing out, all the NA values with that median value. The other approach is you could use scikit-learn's own imputer libraries, right? And impute them with median, mean, or whatever values you feel like. So I'll show you both the approaches. So when calculating median on, or maybe imputing value on your own. So I'll calculate the median. Total bedrooms dot median, right? And then sample. I don't want to mess up the original one. I'll use the scikit-learn's imputer library. That's why I'm assigning it to a different name. Sample incomplete rows. And I'll fill in all the NAs with this value. In place equals true, right? Oh, I should first grab the values. I thought I already did that. Sample incomplete. This is going to be all the rows where it's NA, like the values are missing out. So I'll do a slicing in here. Housing dot is null dot any, like anywhere where it's null across all the columns, even though we know it's across just total bedrooms, but why take any chances? Always keep your code as generalized as possible, right? So that's one way of filling in all the total bedrooms with the median values. The other approach, that is using scikit-learn's, since there are already so many libraries and functions out there, I don't see any point writing down your own logic. Using scikit-learn's imputer class, right? But then it's always important that you know what's the inner line story, what's the underlying process or uh, procedure that's actually happening. So earlier, this imputer should used to be under scikit-learn's pre-processing class. So anytime I would do use an imputer, I would do sklearn dot pre-processing import imputer, right? But since the release of version scikit-learn's 20, I guess, it has changed, and they have changed the APIs. Right now, it's they have created a different class altogether, scikit-learn.impute, import simple imputer. I'm not sure if it's 20 or something. We can check out, like, what's my current version. Okay, while that happens, let's get back to work. So the way to impute values, we'll use the simple imputer, and I'll instantiate it. And the strategy I'll specify as median, right? Now that's created. Let me see if it shows. Okay, forget it. basically the present API has it under the impute class, right? So now I'll change, and in fact, before messing up with the whole data set, let me create a subset out of it. So I'll grab all the numerical attributes in here, and I'll drop the categorical one, which was just the ocean proximity. PROXIMITY, right? It's strange because none of you have so far asked me that I'm doing a drop and then assigning it. How is it that it's not, dropping it on the actual data set? Well, that's because since you guys didn't ask, I'll answer it on my own. Basically, I'm dropping this, but I'm not actually dropping it from the housing. I'm assigning it to a new variable. So the actual data set remains intact, and the rest all is stored in here. And in here, I'll use the scikit-learn's imputer. And if you remember, scikit-learn always has these three methods: fit, transform, and fit underscore transform. Fit, wherein you're doing some computation; transform, wherein you're doing some bit of transformation, that is after some computational logic that you have applied; and fit underscore transform, when you want to have your computational logic applied to it, and then the values being transformed. Right now I just want to compute this computation logic across all the numerical values data set. So there we have it. Now if I want to know uh, the median of each attribute and the store, I mean, if you're curious to know, like this, how exactly the imputer has been scaled out, you can call in the statistics underscore method. So I'll write down. So imputer basically computes across all the attributes. So based on the strategy that you specified. So if you want to know the, if you want to see this across all the attributes, just call statistics underscore method. All right, I'll show you guys. Imputer dot statistics underscore, and this would give you like across all the values, what's the median across all the attributes, all the housing underscore num attributes, all the attributes under housing underscore num sub data set that we created, right? And then if I'm to cross verify this, I have this in here, and I could do the same way we calculated in here across the entire housing data set, and I can check with the values that they have, and it would be pretty much same, right? So there are a number of ways of achieving the same result. It's all on how you address the problem. So you can use scikit-learn's or scikit-learn's own imputer class, or you can write down your own logic. So right now we are just doing some bit of cleansing, handling some of the missing values. So now let's do a full-fledged operation. I'll create the imputer and then transform these values. We already applied the fit method. We'll now call in the transformation. So I'll do imputer dot transform, and then I'll pass in the housing num, and I'll store it in the variable x, right? And in fact, I'll add in the comment. Using the imputer we created, let me create a markdown block. We created above, right? transforming the training set by replacing the missing values by the learned medians, right? And there you go. And let's call it housing transform housing underscore tr, and grab all the values in a data frame x, and columns would be same as the columns in housing num, right? And so we'll use housing underscore tr as the transformed housing train x data set, or the training data set housing underscore tr, right? And if you want to cross check if it doesn't has any cross check for missing values, if you want to do, I mean, you should always do, you should always cross check your approaches. As long as you're there in a Jupyter notebook or spider like session, it shouldn't be a problem to iterate over some code logic as many times you want, right? Let me do a head. So there are no rows at all. Even if I remove the head, there's no rows with missing values. There's no row that has is null set out to be true across all the attributes or columns. So now that we have a complete data set under housing, oops, here, yep. This one has all the numerical attributes. Remember, we removed the categorical one, but we do want the categorical one as well. So in fact, now let's look into the categorical one. I'll mark these as steps. So we did some cleansing in here. So I'll add in a block in here that says some data cleansing, right? Now this one would be handling categorical values, right? Now let's get these under a new data frame. All the categorical values that we excluded earlier, ocean proximity. Okay, all right. Okay, nice. So now you can, there are a couple of ways of handling categorical values. One approach is you replace each of the category by an index. Like you can have one assigned to this category, two to this, number three assigned to the third category, right? And you can use label encoders, one hot encoders. These are approaches, and they already have libraries under scikit-learn. But that's kind of like very longer route. The other approach is since you're already in pandas, you have all your data set already in pandas data frame. The very first shortcut you could do is have this transform into zeros and ones and twos and three, like numerical labels with respect to each category using the pandas factorize method. Not many people use this, but when I'm working with pandas data frame and I have like straight away exclusive, mutually exclusive categories, I don't even go about using the label encoders and one hot encoders. But let's look into every approach. So starting first, we'll look into pandas on factorize method to convert them into categorical features, because right now it's all string. We need to set them into a category. So how do we do that? We call the factorize method. So I'll use the housing cat, and I'll rename this. I'll name the new as housing cat encoded, right? And one variable for storing all the categories. And then I'll pass the housing cat to the factorize method. I'll call the factorize method. I won't pass in, right? And yeah, now if you see the housing cat encoded variable, like if I slice down like the first 10 elements, first 10 instances, these are their categories. Now, if you are not really sure of which one represents 0 and which one's 1 and which one's 3 and which one's 2, you'll call the housing underscore categories, the one we created in here, right? So starting with the indexes, less than 1 hour ocean string is categorized as label 0, near bay as 1, near ocean is 2, inland is 3, and island is basically 4. 0, 1, 2, 3, 4, right? So across 5 categories, this is how the categories have been labeled. So for the first 10 instances, we had these values. 0, nearby is 1, near ocean is 2. So it's the same, right? So that's one way, right? Now we'll talk about the other way. The other approach is using the scikit-learn's one-hot encoder. So the other is, what did I write here? Using pandas. Now here using scikit-learn's one-hot encoder, right? Now one-hot encoder by default returns a sparse array. This is something you should know. But to convert it into a dense array, you'll have to again transform it into an matrix or an array. So at that time we'll kind of use the two array method of pandas. Pandas. Okay, I'll start writing from sklearn dot preprocessing import one hot encoder, right? I'll set out an instance for this. And now to transform our housing category values, I'll call this one hot, right? Encoder dot fit underscore transform, and I'll pass in the housing categorical variable, or maybe housing category. And actually you should pass in the encoded value, because straight away strings won't be handled. You'll have to first pass them through label encoding, and it's only then you could use the one hot encoder. Since we already have all the labels encoded in 0, 1, 2s, and 3s, now we'll encode them with respect to one hot encoder. So since no one asked, I'm assuming everyone already knows what's a one hot encoding approach and what's a label encoding. Let me know, guys. If not, I'll explain like in a short brief how exactly we do that. Anyway, I'll explain. So I'll open up the Excel now.
Bro, you just give them a little intuition. However, I'm
Yeah.
providing them in the form of videos.
Sure, I'll explain in very layman language how
Fine.
exactly things are. So let's say you have labels as A, B, C, D, C, D. Let's say you have these labels, and one way to convert these string values, since your machine learning model always works on numbers, the machine never understands a string, right? You can either convert these into some ASCII code, which is again a number, or some bit of logic that you have on your own, but then you can't really work straight away with strings. You need to have them convert into numbers. So how do we handle that? We assign them with some labels. One approach is label encoding, wherein you pick up one label and you start assigning them with some value starting with 0. So I'll assign A as 0, B class as 1, or B string as 1, label 1, string C as label 2, string D as label 3. This is nothing but simple label encoding, right? अरे यार LABELENCODNG. So that's one way of label encoding. But imagine a scenario wherein you have like some bit of ordinance in the labels, right? Imagine it, you have all your temperatures of a thermometer stored in. You have something as high temperature, right? You have something as medium, something as low, very low, very high, I don't know what not. There could be many cases, right? But there's some bit of ordinance, right? At that point, you would want your label encoding, and imagine a scenario wherein you need your encodings to be, in the same ordinance fashion, like maintaining the same order. So you can't just randomly assign them some labels, right? So I mean, there's no way you can set out the ordinance. The other approach is you set out the label encodings first, and then, pivot them so that there's a relation. So I'll explain. So imagine if I'm, computing, label encoding these as some random values 0, 1, 2, and 3, even though the ideal, order should be very low as 0, low as 1, medium as 2, and maybe high temperature as 3, right? Let's keep it just high, right? So since we couldn't do that, the next thing we'll do is we'll pivot this, and every value within this column will get transformed into column headings. So I'll now have these values as high, medium, low, very low. And now I'll do a one hot encoding, and I'll assign 1 to every instance where it was just high. So for a row where it was just high, I'll have this 1 and the rest all as 0, right? Now, if you see the label encoding for this one instance, it's 1000, right? That's label encoding together, and this is one hot encoding. And for a case where it's just medium, the rest are 0. For medium, it's 1, right? Similarly, for this, it would be 0, 0. For this one, it would be 1, 0. Right. So this will become 0, 1, 0, 0. Okay, Excel doesn't let you put 0 ahead, but then, okay, maybe I'll change this to string. Oops. Anyway, don't have time for that. So this would be 0, 0, 1, 0. This would be 0, 0, 0, 0, 1. So now if you see, they all have like distinct label encodings, and you can kind of, set them out in any ordinance fashion or any way you want, right? And not just in scenarios wherein there's some bit of ordinance in the labels, even when there's some bit of relation or correlation between the labels, it's always suggested that you map them into one hot encoding fashion, right? So you basically do all the label encodings, but in a way wherein you're marking it 1 only for the case where it's just that particular category, right? And for the rest, you're keeping them, but you're assigning them as 0. Similarly, for the case where it's true, you're keeping it 1, and for the rest cases, you're still considering, but you're marking them as 0. This is what we call as one hot encoding, and simple mere label tagging is what we call as label encoding, right? And we can achieve label encoding like functionalities using pandas factorize method, and that is what we have done so far. So far, so good. Any doubt? Do let me know. No? So we will use these label encodings, and then we'll pivot them and have all these values as distinct columns, right? And have these values in 0 and 1 fashions. One hot encoding. The reason it's called one hot encoding because only one of all the cases is true. The rest all it's false, right? One hot among all non-hots. Anyway, so we are using scikit-learn's one hot encoding. You can ignore the future warning. Doesn't really matter right now. Future warnings are basically some change in their APIs, but then that's okay. Unless it has deprecated, I'm not really worried about it. Right now, notice that. In fact, let me show you guys. Usually, when you do a one hot encode, you get a sparse matrix, right? Which is a 1D array. This is like a one-dimensional array of a sparse matrix of 16,512 elements parsed in row format. It's a one-dimensional array. But your fit transform method basically expects a 2D array. That's why I had to reshape this. I kind of did in the wrong way. Should have been one row, one column. Right. Cool. So you'll eventually, you'll have to return it into a dense array because one hot encoder always returns a sparse array, right? This is a whole different data structure we can't really work with. You'll have to at some point, typecast it into a dense array. So to do that, we use the pandas two array method. So I'll use the two array, and there we have all the dense array. Okay, I'll write in the note since one hot encoder returns a sparse matrix, need to change it to a dense array, right? All right, so far so good. Now let's plug in these two, right? All the numerical and categorical, since now even the categorical values we have them as arrays, all numbers, array of all numbers. So we can kind of club them together. And in fact, before we do that, you would want all these transformations to happen in a pipeline fashion. If you're setting up a machine learning model for production environment at some time in future, you won't go about doing all these computations manually, at least like creating these custom features on your own manually, right? You would want to set it out into a pipeline. Or maybe you could create a function that does all this, right? Something like scikit-learn, wherein you pass in, wherein you call the fit underscore transform method and pass in your data frame. It does all the attribute creation and everything, all these custom transformations on its own. But to do that, remember I even mentioned this in our first classification problem. We use the scikit-learn's base estimator and transformer mixin library to create our own. So anytime you want to write your own machine learning algorithm into scikit-learn, you'll have to use the base estimator. So next up is custom transformations that we'll be looking into, right? So from sklearn, I'm gonna import from the base library all these base estimators to create our own, algo logic, wherein when we pass it through the fit underscore transform method, it does all this, transformations in one go. So that next time we can use the scikit-learn's pipeline library and have this set up as a pipeline end-to-end solution for our machine learning model. So I'm calling in the base estimator and transformer mixin. This is like a must-have. You need to import these two libraries, and these will be passed in as arguments or parameters to your new inherited class that you'll be writing down that with whatever logic you have for the transformation. You need to pass these two as the arguments. It's only then it's applicable to have fit and transform method, right? So I basically want, so I'll create a class of combined attributes, or adding combine attributes adder, right? And I'll pass these as arguments, right? We'll set out an init method, a fit method, and a trans method. We'll declare that, and it's all good to go. You have your class ready to be called in. And so I first need, I want to add bedrooms per room, right? That is something it should do beforehand. And for transformation, I would want it to calculate the rooms per household and the population per household, right? And if bedrooms per room is already there, maybe, calculate, otherwise create a new fresh one, right? That's all we did, 3 custom features. Yeah, somewhere in here, yeah. These 3 custom features. So first thing, we'll add in these. Add bedrooms per room equals true. This is when no argument has been specified. So I'll create bedrooms per room. Right. We'll create a fit method and pass in the X and Y. And sometimes you won't even have to pass in the Y label. So by default, I'll set the Y value to be none. Right. And this should return just nothing. There's no, computation that we have. Nothing to do here. Just want some bit of transformation. So I'll call it transform. And in here, when we pass in the X and Y's, first things first, calculate the rooms per household. So rooms, I'll grab all the values for the, let me grab the index labels because it's easier to slice them up. So rooms index is basically 0, 1, 2, 3. Bedroom is at index 4, 0, 1, 2, 3, 4, right? And the population has index 5. Household is at index 6. I basically need these, so I'll assign these some index values because I'm too lazy to write down the entire column names. If you're too energetic, write down the entire column names. I don't mind. Rooms index, bedrooms index, population index, and household index. I'll just re-verify. So it's Rooms, bedroom, population, household. Rooms, bedroom, population, household. Rooms, bedroom, population, household. 0, 1, 2, 3, 4, 5, 6. Right. So I'll add in 3, 4, 5, 6. Right. Rooms IX. Similarly, grabbing all the rows. Index, household IX. Right. Population per household. And then again slicing them, grabbing all rows at the population index, right? Dividing them by X, grabbing all rows by the household index, right? Now, if bedrooms per room is added, this is why I added if rooms equals true. If it's there beforehand, self dot add bedrooms per room, then I'll add in this feature, bedroom per room. This is equal to slicing X based on bedroom index divided by X sliced on all rows and rooms index, right? If there's any doubt so far, do let me know right away. And I'm concatenating all these values. So X, the rooms per household, population per household, and the bedrooms per room. And if it's set to false, I'll just do the concatenation of the rest. Copy, paste. Right? All right. Now I'll create a new variable and I'll instantiate this combine attribute adder that we created. And I'll set the add bedroom flag to be true. In fact, I'll keep it to be false and then see how housing attributes transform. So this would be housing extra attributes, calling in the same instantiated variable and the transform method, and I'll pass in the housing dot values. Super. Okay, now let's put this into a data frame and see how exactly it looks like. So I'm using the same name for the data frame that we are creating. Columns will be same as the columns we had in housing, right? Plus these 3 columns that we created. So remember in list, when you do a plus wise operation, it's basically concatenation, and it's a new list with concatenation of the two. So this is rooms per HOSCHOLD household, comma, population, cool. Now let's do a head on this housing attribute head. All right. So now we have a well-prepared data frame with some more custom features, right? And this one didn't had, like the add bedrooms flag turned out to be true. Just to show you guys how exactly I'm planning to have this projected, right? Now since we have this, method laid out using scikit-learn's base estimator, our own, class declared in scikit-learn's base estimator, we can set up a pipeline now. So next up, setting up pipeline for all the pre-processing, but pre-processing of just numerical attributes. We'll combine the different pipelines together. I will basically create one pipeline for all the numerical attributes, and then we'll create one pipeline for all the categorical attributes, and then we'll add in both the pipelines into a new pipeline, right? Like a pipeline of pipelines, right? And then we'll call in that pipeline every time we want to, retry a different machine learning algorithm. We just need to transform the data by just passing in the X and Y's to that pipeline. Let me just write out the heading as setting up pipeline for all the pre-processings. Superb. This is something we have already done. So by now you guys should be familiar with sklearn.pipeline. I'll import pipeline. And we would also want to, scale up, like all the values should be scaled. I mean, it's a good practice. You can add in more to your model's accuracy if you just scale all the values within the same range. So I'm calling in the standard scaler as well. So far, so good. I'll create a pipeline, num pipeline for all the numerical attributes. All right. So first step in our pipeline would be to handle the missing values. For that, we have a simple imputer. I'll call it imputer, right? I'll specify the strategy, to be median. So here, for the next would be to add these attributes, rooms per household, population per household, right? I'll call this attributes, that's attributes. And in fact, that's a big name. Let me just call it attributes add or attributes add. Okay. And I'll call in this new class that we declared, combine attributes adder, right? This time I won't set any flag for adding bedrooms because by default it's set to true. So by default it will create one more feature like bedrooms per household, bedrooms per room, right? I didn't include that just because out of laziness. Otherwise I would have to write another name. But anyways, yeah, I'm lazy. Third step would be to scale the values. So I'll call this as standard scaler. And we'll call the standard scaler we included here, right? And there you have it. You have set up your pipeline for all the pre-processing of all the numerical attributes. Next time you need to just pass in to the fit underscore transform method of this pipeline, num underscore pipeline, and all your transformations would happen in one go, right? Such a nice thing. I mean, I always recommend that you should set out pipeline for all the transformations right after you're done with the EDA part of the new data set. It's a good practice. So I'm calling in the fit underscore transform method and I'll pass in the num housing underscore num, which is basically, if you remember, all the fields except for the ocean proximity, all the numerical attribute, right? And if I, there we have it. So now we have a X data set that is like all numbers. You can just pass into any, machine learning algorithm you want to try out, and it would work. But right now we haven't included the categorical, values. So we'll set up a pipeline for handling the categorical transformations as well, right? Okay. In fact, I'll create another transformer, just like we created for the numerical attributes. We'll create another transformer for handling the categorical attributes. So I'll create another class. I'll call it. And before we do that, in fact, there's not much. Yeah, I don't think we need to write down the logic for all the categorical transformation. It's just encodings that we did, right? But we would want, so when you pass in the housing data frame, like the original one that we included in the very beginning, it should automatically, segregate all the numerical ones and the categorical ones, and then call in this num underscore pipeline, the numerical pipeline that we created just on the numerical ones, right? We are just easing out our own task. Otherwise, you'll have to, manually separate numerical ones and then the categorical ones, and then on the numerical ones, you'll pass in the pipeline. There's no point. You can write a pipeline that separates numerical and categorical as well, right? So I'll call it data selector, or maybe data frame selector. Again, I'll use the base estimator and the transformer mixin, right? Passing in those two values as arguments. And now I'll create the three methods: init, fit, and transform. And we are done with our class. So for initialization, initially they should be assigned with some column labels, like what all to be considered as one data frame and the rest as categorical or different data frames. So I'll give it the attribute names as the argument, right? So anytime you call in data frame selector, fit underscore transform method, you will have to pass in the attribute names. So I'll set this attribute underscore names equals attribute names, no change. And we don't have anything in fit, but we have to declare it. So X, setting Y to be none by default, because sometimes you won't even have Y label. Return self. Again, do nothing. It's basically a transformer that we are creating. So in the transform method, we'll basically, grab all the column names by their value. So remember just how we have value underscore counts. So let's say if I am to grab, fetch any value, any value within a column, I just call in the values method. Remember, this gives me all the values. Other approaches, you could just call in this, but then this returns a data frame like a one-dimensional array. I just want a simple array without any indexes, row indexes, right? So we'll just call in the values method in here. So we'll do a similar kind of thing in here. It should return X sliced down by the column names that we specify. Attribute names dot values. And yeah, that's all we need. Right now, let's create a complete pipeline. So complete pipeline. So first thing that pipeline would do, it would pass in through the transform method of the data frame selector, wherein we'll give it all the, wherein it will segregate the numerical from the categorical columns, and then it will apply the numerical pipeline and the categorical pipeline accordingly, right? Okay. I'll need one hot encoder, so I'll import that. Or maybe I have already imported that. Yeah, we have. So let's just start with numerical attributes. I'm basically creating a list of all the column names which are numericals, and we already have all the numerical a data frame with all numerical values. So I'll just do a columns method, and they'll pass in it through a list, like a wrapper. So we have a list of all the column names and the numerical attributes, and these are all the columns that have just numerical values. And similarly, I'll create one for, and this is basically ocean proximity. We just have one. Proximity. Okay. Now to call in the numerical num pipeline, and I'll call this selector, right? Are you getting why I exactly included the data frame selector, created a new base estimator class in here because of this, so that it segregates numerical pipeline and categorical pipeline, and we don't really have to do this part also manually. So everything is pipeline now. I'm sorry, imputer is under simple, imputer strategy is median, right? For adding attributes, attributes adder, right? And then the last step, scaling them. So I'll call the standard scaler. That's a numerical pipeline. Now for the categorical pipeline, we'll call the selector. Oops. I'm sorry. Data frame selector. And here I'll pass in the cat attributes, which is this list of column name that has all the categorical attributes. In our problem statement, we just have one that's called ocean proximity, right? And then we just need the encoding that we did, right? And it has to be categorical encoding. So we'll call the one hot encoder with sparse argument set out to be false. Because remember, we by default, it gives you a sparse array, and we basically want a dense array, right? The way you can do this is just by setting out the sparse argument in here equals to false. I didn't do that initially because I wanted you guys to know that this is how exactly this happens. Sometimes you might face these issues and you'll end up going to Stack Overflow. I have passed back way in the past, so I know this error. So I'll call this encoder, categorical encoder, calling in the one hot encoder with sparse argument set out to be false, right? And yeah. So now that we have all our pipelines set up, Now we can create a union of these pipeline, basically a pipeline of pipeline. And to do that, we have a class called feature union. That is again under the scikit-learn's pipeline library, wherein you can club multiple pipelines into one bigger pipeline. So I'll import feature union, and feature union say we'll create this union of these two pipelines. So I'll call this full pipeline equals feature union, and you have to set out the transformer list and pass in the pipeline in here. So the first, I'll call it num pipeline. I'm keeping the same name, and I'll pass in the num pipeline. This would be a categorical pipeline. So many spelling mistakes. Right. Cool. Now that we have a whole, pipeline prepared. Okay, let me just execute this block and we'll work here. So now that our whole pipeline is prepared, now anytime you want to, try out a different machine learning algorithm, you don't have to, re-prepare the data. Because sometimes while trying one machine learning algorithm, you'll do some bit of transformation that might actually affect your other the approach that's out there in other machine learning algorithm. Different algorithms have a different way that they intake the data, and for that part you have to prepare the data. You do some bit of data preparation before fitting it to any machine learning algorithm, right? But right now you just need to change in the steps within the pipeline. And if there's no change, just call in the full pipeline and it's all done. Makes your task so much easier now. So now if I'm to, create or prepare a data set, I'll call it housing prepared. I'll just pass it in through the whole pipeline. Right. Fit underscore transform. And I'm giving it the original housing data set. And there we have it. All the transformations done. You didn't have to do anything, right? Now comes the part wherein you can try out different machine learning algorithms. Everything we have learned so far, all the regression techniques, all the regression algorithms. Now you'll try, select and train the best model. It's not that straightforward when you're actually, working on a machine learning problem end to end. So far, we haven't even started the machine learning model. It's now that we'll be, trying out different machine learning models. All right. So first things first, anyone has any preference? Or I'll start with linear regression. No answers. Okay. I'll start with linear regression. sklearn dot linear model. I'll import linear regression. Oops. Right. I'll call this linreg. Basically instantiating it. Okay. Now to pass the prepared data set to it, and oops. And remember, we kept y labels separately as labels, I believe. I don't remember, was it labels or housing labels? We dropped median in price, housing median house value, and kept everything else. And then we saved I think it was under the name housing labels. Let's see, LAB, tap, tap, HOU, tap, tap. Okay, it was under housing labels. Let me just cross verify. Housing labels. So yeah, median house value, right. All right. So passing in all the X and Y's to our linear regression model. And there it's trained since it's a very small data set. So yeah, there we have a linear regression model fit into a California housing price prediction. Now you can predict it on any new data set that you feel like. And in fact, let's try putting in the machine learning algorithm also as part of the pipeline, or let's try a full pipeline on few training instances and see how exactly it's predicting, and then maybe later we'll try fitting in these also as part of pipelines. That is when you're actually deploying it to a production. You have finalized your machine learning algorithm. You have finalized the hyperparameters, how exactly do you want to tune them. You can kind of fit them also as part of the pipeline. Then it's an end-to-end solution for your production environment. Right now we are still experimenting with what machine learning algorithms to pick. So for now, I'll run the full pipeline on few of the training instances, and then we'll compare the prediction through linear regression model with the actual labels that's there, right? So trying the full pipeline on a few training instances, right? Let's call it some data. Like how I have this habit of naming them as some data, some digit. Even in MNIST, I remember I renamed it to some digit. So yeah, slicing up the housing data set, I'll grab some 5 values, right? And some labels. These would be the labels of these data values that we grab. Right. We grab some instance values and their labels. Now I'll pass these through the full pipeline. It's okay if you just pass it to fit underscore transform or just the transform, because we know there's nothing in the fit that we define. So it's all transformation. Some data, right? And now let's, oops, okay. Let's print the predictions now and the labels. So the predicted values through our linear regression models and the actual labels. Predict some data prepared and actual labels. And here I'm gonna just list them, some labels, right? Let's compare. So it says across all the 5 values, it says for the first one around 209,526 US dollars, while the actual label was 166. For the second one, it says 455,497, but this one says like 500,001 US dollars. So we see that there's some bit of errorness in this. So let's compute the mean square error. How much exactly is the error rate? How exactly it's deviating? So we'll import the mean squared error, right? And I'll call this housing predictions linear regression model dot predict on housing prepared, like the entire prepared data set, and then we'll see how much is the mean square error, and then we'll do a square root of it, and then we'll see how much is the root mean square error, right? So I'll call this linear mean square error. Oops. Right? Passing in the y labels and y train basically are housing labels, and y labels and y predicted values. So housing labels and housing predictions, right? This is similar to what we have been doing. This is nothing new. We pass in the y and y pred. Remember, y train and y pred, it's the same thing. I'm going to call this root mean square error, linear RMSE, and then numpy square root of linear mean square error. Let's see how the values look like. So there's clearly a lot of root mean square error. So let's try a different algorithm then. Maybe a decision tree. In fact, I don't know if you guys remember, if you don't specify any parameter to a decision tree, it's always bound to overfit. Remember? So if I just don't pass in any stopping criteria for my tree-based algorithm, root mean square error should return 0, right? Because it's mapping every data instance value by value, instance by instance, right? Overfitting every instance. So that way we'll be sure that at least the root mean square error is being computed correctly, right? So I'm not passing in any stopping criteria or parameter for this. I'm letting it to overfit just to see if it's actually reporting as 0 as the root mean square error. Then ideally it should. Let's see. Passing in the housing prepared data. Where is that? Housing labels. Right. Housing predictions, right? Tree reg dot predict, and then I'm gonna call in the housing prepared, right? Tree based mean square error, passing in the housing labels, y train and y predict, housing predictions, right? Their RMSE would be the square root of this. Right. Again, so our hypothesis was true. At least the main square error computations, right? It's just that it's not really fitting out linearly. So maybe the data set is not really linearly dispersed out. That's why a linear model is not working that well, and there's such a huge root mean square error rate. So let's try out cross validation on the decision tree now, right? Markdown. And since we have this pipeline setup, the moment you get this notebook, feel free to try out different algorithms, different regression algorithms, right? So I'll import the cross val score now. Okay, I know it's already past 12. Just bear with me for a couple of more minutes, guys. I'm pretty much done, and then I'll hand over this notebook to you guys for you to practice or try out different algorithms. I'll just show you one more, and then we are good to wrap up. But yeah, while I'm writing this out, if you have any doubt, do let me know. Housing prepare, housing labels, right? Cross validation, we'll keep it to 10 folds. And the scoring method would be negative mean square. Why negative mean square error? Because whenever we specify negative mean square error, it basically takes into consideration the root mean square error, right? So negative mean squared error. And now that we have scoring on in negative mean square error, the moment you know calculate the square root of these values, you'll get the actual RMSEs. The other scoring mechanisms are accuracy, just mean square errors. But then if you calculate mean square error, you'll have to compute like a negative of it, and then again take a square root. Oh, three. Let's save all the scores as well. Key error, neg mean square errors. Okay. Is there any spelling mistake? Because I'm pretty sure this is a squaring mechanism. NAGMEANSQUARED. Yeah. So scikit-learn cross-validation feature will, expect the utility function to be always greater than the cost function. If it's a utility function, the greater the better. If it's a cost function, the lower the better. So the scoring function is actually the opposite of mean square error, and that's why the negative MSE value. Right. Now let's display the scores. So just to give you guys an idea how values are deviating. The standard deviation. In fact, I'll create these into function. Okay. Okay. Yes. All right. So that's the score. The average score is the average root mean square error is about 69,483. Standard deviation is about 1442. Okay. This is even worse than our linear regression model. The decision tree has a score, approximately 69,483 plus or minus 1442, right? Now let's compute the linear regression score as well. This is pretty bad. Oh, that's probably because we tried to overfit. We haven't really, the tree is mapping out everything instance by instance. That's why. Your tree based model is not really of any use unless you map it out in a more generalized way. So calculating all the linear regression scores, housing, prepared, housing labels for tenfold. Scoring is again the same. Negative mean, skew UARET squared, error, right? Yeah. RMSE scores would be and then we'll display the scores. All right. Okay. This is somewhat better. I wouldn't say it's like a really good model, but yeah, there you have it. The task for you guys would be to try out random forest regressor here. So I won't do that, but I'll leave it to you guys to experiment with it and then see if even random forest regressor doesn't works well. Try out some other, ensemble techniques, because for this particular problem statement, California housing price prediction, ensemble models have, kind of outperformed. And you'll pretty much get the very good, model through random forest regressor. And maybe once you finalize what machine learning algorithm you're going to use, do hyperparameter tuning using the grid search method, right? So I won't do that. Okay, if yeah, I'll do that. You guys are okay with another 2 minutes? Won't take even 2 minutes, honestly. All right. There we have a random forest regressor. Now, okay, I'll just copy paste. I'll have to calculate actually. Housing predictions. Right. Right. Well, this is somewhat better. Now you can even try out different, hyperparameter tuning, and you'll kind of get the better, optimal regressor model in here. Fine tuning. So let me know, guys, if you're okay. I'll explain an exemplary problem wherein how exactly you do fine tuning of the model. Otherwise, I'll just wrap it up. I'll wait for your guys' comments on this. Hello. Okay. Cool. Then I'll leave it to you guys. Let me know in our next class if you face any challenges, right? In with the grid search and fine tuning of the model. We have kind of like random forest regressor performing better than the rest too. So the next step would be to fine tune the random forest regressors. So basically you would tune the hyperparameters of random forest regressor. Try out different estimator values or bootstrap, right? Or max features like that. Yeah. So that's all for today, guys. We picked up a problem statement and we prepared an end-to-end machine learning, algorithm, machine learning solution around it. If you have any doubts, let me know. Otherwise, I'll see you guys on Saturday, wherein we'll discuss about dimensionality reductions. Most welcome, Hari.
Hi, sir.
Hi, bye.
I'm understanding concept, but coding is very difficult for me. How can we? Already,
Mm-hmm.
I'm trying to understand, but you are writing so much of coding, but I'm not getting that much of coding.
Yeah, I get that. It happens at the very beginning, but so I'll tell you. Any moment you feel a difficulty in understanding, do let me know so that I can explain how exactly I'm, thinking the logic and before coding it into any programming language, Python or Scala, anything, right? So you'll get the idea how exactly you're supposed to think, how exactly you're supposed to prepare the logics. You know Python for now, at least you know the basics. You know how NumPy and pandas work. You pretty much know everything. That's why you're able to understand. The reason you're finding it difficult to think through it while coding is because you haven't really had much of an experience while practicing or maybe doing more of these problem statements.
Okay.
I had this idea, ठीक है, यहाँ पे it's not working. I'm supposed to scale this. Okay, here it's not. It's all string values. I'm supposed to transform this into encodings
Okay.
because I have already practiced for like couple of times problem statements like this, regression and classification. So you'll get the hang of it the moment you start practicing more and more. But if you're facing challenges in understanding any concept, like the one I did here, I concatenated two strings in here. If you know how string concatenation works, then it's okay. But if you don't know how even a string concatenation works, then it would be difficult for you, right? So that's a underlying concept. So if you're having difficulty understanding concept, point me out right then and there, right? Like in encoding, if you're not really familiar with encoding, I'll explain right away, right? But if you're not familiar with how exactly to create a data frame and NumPy, then it might be an issue. You'll have to start with the basics, what pandas is, what NumPy is, how operations in NumPy works, right? Go
Okay.
through our initial class sessions of NumPy and Panda. That would be really helpful. After
Okay.
that, it's all exploration. I'm exploring numbers, opening up every attribute, every column value, seeing what values it has, right?
Okay.
It's simple. It's not really that hard. You're facing that initial beginner's fear, which is very obvious. We all have gone through it, right? It's very obvious. Just hang on to it and keep practicing. You'll get the idea about the approaches. It's all about practice.
Okay, sir.
And if you're having difficulty with Python programming, I would suggest you try out this Python programming. I don't know if I showed you guys. Practicepython.org. It's a really cool site with 36 example problems, like very basic, finding out the odd and even, some list operation, division operation, string wise operation. The chilies basically represent the difficulty level. So if you're able to do at least like 15, 20 of these, you're pretty much, you have good hands-on of coding at least. And then it's all about pandas and NumPy, how the libraries and the methods they have. You just need to use them and prepare data and then put into your machine learning model. For the logic, the underlying logic that's there in machine learning model, we already discussed when we were talking each algorithm specifically. So go through those sessions, you'll get the idea how exactly each regression algorithm is different from the other, how exactly each classification algorithm is different from each other.
Okay, sir.
Mm-hmm. In fact, if you guys are okay with another 5-10 minutes, I'll show you how to do hyperparameter tuning as well. I understand it's your holiday as well. It's even Raksha Bandhan on the same day, so no issue. I'll do it on the notebook before submitting it to you guys. That's just one last thing that's left out. Let me know if you guys can stay for another 5-10 minutes. I won't take more than 5 minutes, I promise.
You go on, bro. You go on.
Okay. So to do the hyperparameter tuning, once you have finalized that, okay, I'll work with this one particular algorithm like random forest regressor. Okay, thanks. So once you're finalized with what machine learning algorithms you're going to do, like this one is performing better than any other regressor algorithm, you'll, start, squeezing out to get the most out of it. So you'll fine tune these hyperparameters. The way we do it is using the grid search. This is again a class library within scikit-learn. So I'll pass in some random bunch of parameters that I want to experiment my, decided machine learning algorithm around. So since it's a random forest regressor, we have already discussed the important parameters that actually, influence your tree-based algorithm, like estimators, number of estimators that there can be, the maximum features that you can create, the basic stopping criteria for any tree-based algorithm. So I'll try out some bunch of parameters and then I'll pass it through a cross validation, and then I'll see at what combination of features the at what cross validation the cost function is at the least, and then I'll pick those parameters and then retrain my model, and then anytime there's a new instance, I'll do a predict method on that with that hyperparameters. That's how you fine tune your machine learning algorithm. So for this random forest regressor, I'll pick a number of estimators, and for the initial, we'll try out some random values. All right, some random values like 3, 10, 30. I'm sorry. And we'll also use max features. Oops. If at any time you're not sure of what hyperparameter the machine learning algorithm has, go to scikit-learn, that algorithms, documentation, and you'll have all the structure and the arguments and hyperparameters with their default values, right? So I'm trying out hyperparameter tuning on number of estimators, the maximum features, and then in another combination I'll try out with bootstrapping and number of estimators, right? This one, and maybe bootstrapping, number of estimator as well as max features. So I'll try out 2 different combinations, and within each combination, the number of combinations the cross validation can think of. So maybe 8, 2, 4, 6, 8 looks good. So that's one set of combinations. So it will run cross validation across all the value combinations it can think of between these 2 parameters. 3 with number of estimators set to 3 and max feature set to maybe 2, and then 3 and 4 in here, 3 from here, then 6 in here, then 3 as number of estimator and 8 as max features. Similarly with 10, 30, like that. And another set of combinations I would want it to try would be bootstrap set to false, because by default it's true. If you see, by default it's always true. So at one point in time I would want to experiment out a scenario wherein the bootstrapping is set to false and estimators values maybe 3, 10, keeping the same values here. You can use any other combination. Max features 2, 3, 4, 5, 4, 2, 3, 4, right? So that's one set of, so basically there's two sets of parameters that I want to experiment out all the combinations. Now to run the cross validation across these. So random forest reg, in fact, it's a big name. I'll call it RF reg, right? We instantiated it. Grid search. And I'll pass in the random forest regressor. For the parameters, I'll pass in this parameter grid that I created here. That is basically a list of all combination of parameters values laid out as dictionaries, right? And for cross validation, I'll set out to be maybe 5 folds. Scoring is going to be the same, negative mean square. So here, dot fit. We'll pass in the housing data prepared, right? And our Y labels. This will take like some time. Shouldn't take more than a minute. So I'll write down the next step. So to get the best, combination, parameters, you call the best underscore params underscore method. So I'll do a grid search dot params, and to get the best estimators directly, like a combination of across all these estimator of all hyperparameters, to get the best estimators directly. Okay, so it's done. If I run the best params meter, I get this combination that gives me the least of cost function. So at this, set of hyperparameters values, like max feature set to 6 and number of estimators set to 30, I get the least of cost function across these possible combinations. So this is the best I have across these possible that I have passed. So you can try out different combinations, right? And to get the best estimators directly, we call in the best estimators underscore method. I'm sorry, it's estimator, right? So this is the set of hyperparameters that gives you like the most optimal one. Bootstrap set to true, criteria set to mean square error, max step no, max feature set to 6. Then what else? Minimum sample leaf set to 1. You can go through it. So this gives you like the best estimators across all the hyperparameter that's out there. So if you look at the cross validation score right now, if at any point you're curious to know how much is the error now, you can do that using the CV results underscore method. So every computation value across all the cross validation for every combination, it's stored under CV underscore results method. So let's save that in this variable CV results underscore, right? And in fact, let me show you each step by step. So I'll have this main score, comma, our params, and so zip function basically clubs together two values as two list values as dictionaries. So I'll cv res, and it's under mean test score. Now I know this because I have already gone through it. I have been using this, but if you're wondering how I knew that this is under the mean test score, it's there in the documentation of, grid search in the scikit-learn library. You can go through it. And then all the parameters under the params key, right? And I'm basically gonna print them out with the square root, of course, because this is mean square error, negative mean square error. So mean score, comma, our params, and there you have it. At different hyperparameter combination, how much was the, root mean square error, right? And we had the least at somewhere in this, right? That's also obvious from the best params that we got. So now that you have your best set of hyperparameters, you have decided the model, you can train your machine learning model based on this set of hyperparameters, based on this algorithm, with all the transformation logics that you decided, and you're good to go. You can deploy it to your production environment. That's an end-to-end process of any machine learning model building, right?
Yeah,
If
it's really great. You took
yeah,
us through the entire.
yeah, it's like the entire end-to-end solution. If you want to further see it in a data frame, I often do this when I'm so if you put this into a data frame, you can export it to CSV, and it becomes easier to share it with your teammates, right? It's easier to share it in a CSV format, and you can use export pandas.to CSV method to have all this stored. So this is under CV res, right? Okay, but I can directly call the CV results. So don't mind the future error warnings. That's the data frame that we want. So it's all in here. Now you can share this, export this to CSV, save it in a variable, some, right? And then using the to underscore CSV method, you can export it to CSV. I won't do that. I'll let it be here as data frame so you can see it. And then you can share it with your teammates how exactly your machine learning model is, progressing over different hyperparameters. That's also one step. So that's all that's there, guys. Let me know if you have any more doubts. No one asked how exactly to decide what hyperparameter combinations to pick. So one last bit. So if you're not really sure how to pick what hyperparameter values, try randomized search CV. So just like grid search CV, there's something called as randomized search CV. That's also there. Randomized. Okay, there we have it. Right, and then it's basically a random combination of all the hyperparameters that you can think of. Or you can decide on what hyperparameter specifically you want to try randomized search, maybe just estimators and max features, right? And okay, you guys have a couple of more minutes. I'll show you one last example. This is like entire thing that's there. Other than this, there's nothing else that we do. Setting out some random integers, and for the params, okay, you feel free to leave out. I'll still have this mentioned in the notebook, but if you're curious and you can stick around, I'll show you guys. I'll keep the session open meanwhile, and I'll set the
Oh. Yeah, what's the difference between SciPy and Scikit-learn?
so there are different libraries. SciPy is more of like how we have scientific calculators and standard calculators. So
Yeah.
that's more like specific to scientific calculations and computation. That's more in depth, and they are more these days. They are more specific, no, more concentrating to the NLP stuff as well.
Okay, SciPy.
Yeah, that's another library, just like
Yes,
scikit-learn.
yes.
So I'm setting out some random integers with value ranging from 1 to 200, right? For a number of estimators, for max features. I'll do the same thing, setting out some random integers ranging from 1 to max as 8, right? That's done. Ref reg. I'll set out some random seed. And I'll call it random search. We are pretty much done, guys. It's all done. I'll pass in the model, your machine learning algorithm, your parameters, right? It's actually under param distribution equals params distrib. For number of iterations, I'll set it to be like 10, try out 10 iterations for each cross-fold, and I'll set it to be like 5-fold cross-validation. Scoring would be same, negative, mean, squared, error, right? And do mention out the random seed since we mention it here. We don't want different numbers or different results showing up, so I'll make this more readable. All right, so once we have that, pass it to fit method with your housing prepared data. Housing prepared and the housing labels. Oh,
Max feature.
really? What have I written? Max features. FEATURES. That's how it's spelled out, right?
Yes.
Ah, I forgot the comma. I'm sorry. So negative means squared. Again, I'm missing out. Oh, yeah. So there you have it. Once you're not really sure of how to pick what values for each parameter, just pick some random parameters and pass them to randomized search grid. Right? This will give
One
you
last
some
question.
result. Yeah, please go ahead.
Yeah, how that tuning happening is, yeah, what's the really mathematics and is there any graph behind that?
So it's simple cross validation. Remember, we do cross validation to see try
No.
out same
Uh,
cost function on
yes,
different
yes.
subsets.
Not about this cross validation, bro. Hyperparameter tune.
So we are trying out different hyperparameters and then passing them through different k-fold cross validations. And then whichever combination of hyperparameter across the cross validation is giving me the least of cost function, whatever cost function you have like RMSE, MSE or MAE,
Yeah.
will be like the best set of hyperparameters.
Okay, it means we are just taking them through a loop.
Yeah, it's if you remember the normal equation we talked in regression,
Yeah.
we kind of hypertune the hyperparameter, finding the least value of theta hyperparameter where the cross validation is giving the least error. The normal equation, you can refer to the previous session. So it's pretty much the same approach. The theta is all these values, theta 1, theta 2, all these values, and across cross validation, we are seeing whether which, at what point or at what cross validation, with what combination, we are getting the least of, cost function. If our cost function is to find the RMSE, at what point we are getting the least of RMSE. This will take some time, but I'll once it's done, I'll share the notebook with you. But that's all there. I have nothing more to take your time. That's all that's there.
Thank you so much, bro. Thanks for your time.
Yeah, most welcome. Okay, guys. So I'll see you then on Saturday.
Thanks everyone for attending your holiday. Also.
Yeah. Thank you for sparing some time.
Okay, guys. Bye. And
Okay.
the video and the notebook with everyone. Okay.
Okay, guys. Bye-bye.